Yeah, today I'm going to talk about 3 episodes of ablative research. And this is some meta-level thoughts about how to do research. So let's directly jump into it. To me, to have um, some research that comes out as an approach, there are 3 ways. The first way is additive. So it's like P plus something. Um, let's see how it performs. Um, the other one is ablative. Um, so instead of plus, it's minus. And the third one is actually a combination of the two. So I call it alternative because it replaces one thing with another thing. So it's both plus and a minus. I'll go into the details of what I mean for each of them next. So the first is additive research. I think this is the most typical type of a research since I was doing it. It's a very natural way to do research. So suppose you have X. You know that X is a well-known, well-established technique. But so far it hasn't been applied to some domain or some pipeline, P. Um, so the research is just about, let's see how it goes if we apply X to pipeline P. And personally, I have done a lot of additive research as or with a graduate student. So for example, never-ending image learning, that's never-ending learning plus image. Web supervised ConvNet, that's ConvNet with some web supervision, and so on and so forth. So this additive research is, I would say, is the best suited for pushing numbers and winning challenges. So this is a story we had when I first graduated from school. We won both visual question answering challenges in 2018 using this kind of research. So with this kind of research, you usually see some progressive bars like in the bottom. So you start with some baselines, you keep adding things to it, and each component will boost the performance to some level, and then in the end, it reaches the highest performance and wins the challenge. Um, but there's a problem. The problem is on novelty, because if X is already well established and well known, then people would expect that P plus X should work, right? Because X has worked so many times, then P plus X is just yet another time it's working. So some reviewers may complain about the novelty. What's a big deal, even if it works? So that leads to the second type of research I want to share, and this is the main research type I would like to share. And this is a meta-level approach I started to take on more and more frequently after graduation. And I'll talk about 3 episodes or 3 examples for ablative research, but there are many more since I graduated. So for example, let's remove one stage for object detection. Also, that's a classical task for computer vision and machine learning. Um, uh, let's simplify the pipeline for self-supervised learning, or let's remove some of the fundamental beliefs about architectures like transformers. So what do I mean by ablation? In fact, ablation is a term defined by Alan Ewell. He's I think very famous researcher, Turing Award winner from CMU. Um, and he was making an analogy of removing things from human body. Uh, and the technical term ablation there is meaning the removal of a component in an AI system instead of a human body or human system, biological system. These days, in a lot of papers, I see it's being used interchangeably with the term analysis. Um, but if we really dive down into details, uh, analysis is actually quite different from ablation. And ablation means a specific, to me, it means a specific type of analysis, which is to remove things. Um, so what is ablative research? It's very simple. Let's remove things. So the process is that Y is a well-established and well-proven technique in some pipeline P. Let's just remove Y from P and see what it is like. And hopefully, the research will find that in P minus Y is a simpler method, but it will retain the similar performance compared to the original pipeline P. And that would be interesting. And one of the biggest motivation for doing this is for simplicity. So, Einstein says everything should be made as simple as possible, but not simpler. And he didn't explain too much about it, as far as I know. But machine learning folks have actually built a deeper intuition around it. It's called Occam's razor. It says that if all things are being equal, then the simplest solution tend to be the best one. And by best, it means it will generalize better. It can be used for many more things. And that's one of the primary reasons. If we have simplicity in our pipeline, that means it will have good generalizability. But simplicity can also mean more things, more advantages. For example, if we reduce the pipeline by a lot, removing some components, it may be more efficient to run the pipeline again because you remove things. It can also be very good for scientific understanding because we have fewer components in the pipeline, then it would be good it would be well suited for understanding the role of each component in the pipeline. And in terms of novelty, I think this is a big advantage compared to additive research, that novelty is much more natural with this ablative type of research. This is because if Y is well established and well proven, then P minus Y should not work. And if we show that P minus Y can work, then reviewers will tend to believe that there must be something interesting or something surprising out there. Let's find out. So in terms of surprise or surpriseness, it naturally leads to some novelty. It's inherently novel. And then third approach, it's a combination of additive and ablative research. But I want to mention this because, well, let's first talk about the process. It's very simple. So you have a P, it's with some component Y, and then X is an alternative technique to Y. So let's just replace Y with X in the pipeline. And these days, if you check the titles for machine learning or for computer vision or even for NLP, just from the titles, you can tell some of the methods are just doing alternative research. So for example, they would plug in one successful technique like diffusion, successful in computer vision, and then try to use it for language modeling. And the alternative also holds, like the opposite also holds. Autoregressive modeling is very successful in language, so let's try it for image generation. So in fact, these are hot topics for today's research. I want to talk about alternative research because I want to make the connection to ablative research. Because there's no free lunch. Well, most of the time, there's no free lunch. Maybe in graduate school there is. But it means that if you remove something in the component, it will most likely not work out of the box. So realistically, there's always some implicit X that comes to rescue, comes to save the day. So for example, zooming out at a very high level, deep learning has been a very successful approach for modeling the world. But the successful recipe is that it first removes some inductive biases. For example, manually designed features for computer vision, but then it adds things too, like a huge amount of data for training, huge amount of compute for training those models. So the important thing I would like to keep in mind is that we want to make ablation as a first-class citizen after this talk. So it's not like let's always start something with addition. So X is successful here. Let's add it here. Let's for some time think about how can we remove things in the current pipeline. So I want to promote this as a first-class citizen. So with this very long introduction and motivation, I would like to talk about 3 research I've done that's quite representative for ablative type of research. So the first one is for VQA. We remove the region features over there. Most of this is removing. There's no addition in it. The second one is replacing the weight transfer after pre-training. It started out with removing things, but then we have to add something back. So it's alternative research. And the third one is we just applied ablative research brute forcefully to some modern denoising diffusion models, and we call it deconstructive process. And this is mainly for scientific study and understanding. So let's move in. So the first one is for VQA. It's a work published in 2020, so it's a couple of years back. And what we mean by VQA as a task is that you have some visual input, image, you have some texture input, that's questions, and the model will have to give a correct answer. So that's VQA for this task. And the pipeline for the VQA challenge winner, and actually for 3 years, the pipeline roughly stays the same, was you have some visual features, so bottom-up attention over there. You have texture features, and then there's some multimodal fusion feature that combines these two features, and then the model outputs something out of this fused feature. And in 2019, the most successful story was that there is a type of new feature called bottom-up attention being proposed there. And the idea there is very simple. So instead of representing images with grid features, like the bottom left here, it tries to represent images with region features. And specifically, it will use multiple spatial localized features to represent an image. And it's called bottom-up because the regions are selected only from image pixels. So this is without top-down guidance from text. So it's not like the text is talking about a head, then let's just focus on the head region. It's pure bottom-up. There's no text guidance when the regions are being proposed for a specific image. And the way they do it in terms of implementation was to train an object detector. And there was a famous object detector called Xinlei back then. They trained it on a data set called visual genome. They add some, there are some additions to it, which is maybe not so important. But given the image, they would do two things on top of the ConvNet feature. So they will do region selection. So they will score regions and then select regions from a lot of candidates. And then it will also do region feature computation, because now you have a set of regions, you have to represent each region with some features. And this idea has dominated leaderboards for 3 years. And to us, the question we ask is, why is it better than grid features? Intuitively, it makes sense because it can localize individual objects better. It's not a uniform distribution in terms of feature representation. It focuses on some important details while not losing some coarse structures. And it can model object relationships explicitly. So there are a lot of advantages. But it's actually not that clear because there are other confounding factors that potentially make bottom-up attention work better than the previous generation of non-bottom-up generation features, non-bottom-up attention features. This is because the pre-training task was different compared to the previous features. It was object detection, not classification. The pre-training data was also different. So previously, classification models are always trained on ImageNet, but for visual genome, well, for detection, it was trained on visual genome. So we would like to have a controlled study to understand whether these confounding factors are playing a role there. So the basic setup we had was we fixed the pre-training task plus the data set. So this is visual genome detection tasks. We fixed the backbone and input size. So this is ResNet 50 with certain input size. We fix the evaluation task and the metric, VQA and VQA score. We fix the overall VQA model because the VQA model is consisted of 3 components. So we just want to study the visual features. We keep other components fixed. And we studied we performed 2 studies with this setting. The first study is, let's just remove the region proposals and region feature components, feature computation components in the network. And then instead, we use grid features from the same layer. So basically, we remove the region R in RCN and make it a CNN. And we find that the grid features we had was actually quite good. It's almost working out of the box. This is comparing the region features that were dominated before and the grid features we had by removing the regions and make it a CNN. And the grid features from the prior models. So classifier network trained on ImageNet is only getting 60 0.8, but we are getting much closer to the region features that was pre-trained on object detection, pre-trained on visual genome. And the second study we had was to improve the pre-training specifically for grid features. And because the pre-trained detector is called RCN, the R stands for regions. So it's likely highly optimized for region level tasks. So our modification was simple. Let's just break some of the region level design. And the specific thing we changed was to remove the spatial representation of regions in RCN. And we do that by applying one by one pooling instead of 14 by 14, a spatial pooling when we compute the region level features. And that's it. We basically did this design. We still have the backbone keep the same. We only changed the pooling operation over there, and we again used ConvNet grid feature for representing images. And what we find is that now the grid features are getting slightly better than the region features. And we can do the ablation that with one by one pooling, we can also extract region features. It's actually worse than the grid features. But if we do 14 by 14 pooling, then the grid features are inferior. So this is validating that one by one pooling hurts the detection and the region features, but it helps the grid features. But with this, we show that grid features can work just as well as regions for visual question answer. And this is not the end, because for regions, one can select n regions, and these n regions can be sparsely sampled. On the other hand, the grid features are usually densely sampled, because for every location in the image, you have to compute a grid feature. So n is usually smaller than h by w, which is the number of grid features. So to make our study rigorous, we further increased the number of region features, so getting a larger and a larger n. And what we find is that initially it indeed helps. So going from, for example, 30 regions to 100 regions, there's some notable improvement in VQA accuracy. But then if the number of regions further increase, the performance saturates. And in the end, even with the bigger n, so it's roughly the same as h by w, the regions of grid features are still at par. So one is close to 64.2. For grid features, we're getting 64.4 here. Yeah, so that concludes our study of grid features versus region features for VQA. But we also studied the generalizability of this finding. So we tried different backbones, different VQA models, different VQA tasks, different other tasks. And for all of them, we find that the generation holds well. And I want to conclude by talking about the benefit of this ablative type of research, removing things. So first of all, it's a simplification because it removes the region selection and the region feature computation operations. We just have image, compute grid features, and we use it for visual question answering. And this is very simple, and especially it can make end-to-end optimization of visual features easier. for vision and language, because region selection and region feature computation, there is some non-differentiable operation over there. This is an advantage for grid features that you can do end-to-end optimization. The second one is about the speed up. So I was talking about ablative research can potentially lead to faster pipelines, and in this case is especially salient because the region selection time is huge. The region feature computation is also huge. So if you remove them, the speed to compute the region feature drops from 0.89 second to 0.02 seconds. So this is like 40 times faster with a ResNet 50 backbone. And I also want to say that ablative research can also win challenges. So for 3 years, the region features were dominating in 2017 to 2019. But in our case, we wanted to promote this work, so we participated in the challenge for 2020, and we find that grid features can indeed perform the best, and we won the challenge in the next year with our improved grid features. But of course, that was not the end of the story. We find that additive research is still quite addictive. So the next year, and I think this is the last year when they hosted this challenge, someone came and they used a combination of both region features and the grid features, and they were able to boost the performance by a lot in the end. So additive research is still the winner in the end. It's also quite addictive to the community. But we are happy that we find an alternative approach, and it also contributed to the last VQA challenge winner. So the takeaway is that grid features are enough for tasks like VQA. So there's no need to go through regions with our research. Well, these days, if we look back in 4 years, we find that it's actually more than enough, because nowadays people do not talk about region features at all. Nowadays, people just talk about pre-training with large language models, and then you adapt the language models for some vision task, a multimodal vision language task like VQA. And this is more than enough to get really good performance or zero-shot performance on such tasks. So that's the first work. The second work is on the surprising effectiveness of attention transfer for vision transformers. And this is a more recent work. We did it last year, and the paper is just released a couple of weeks back, and it's going to be presented in this year's Europe's. I want to first, to talk about this work, I want to first talk about how pre-trained models are used today. So to me, there are 3 ways. The first way is to directly use the model's output. So for example, you have some so-called foundation models, and then these foundation models can be used to generate captions, segments, images. Those are vanilla usage of the output, but there are fancier ways to do it. For example, you can do prompt engineering. And the second way to do it, to use it, is to compute features. So for example, one can do linear classifier, add a linear classifier on top of the features extracted from such models. And there are fancy ways to do it too. For example, attentive probing. So that's like a weighted combination of the features, and you can extract the features from multiple layers of the deep neural network, multiple scales for vision as well. And the third way is the most, I would say, intrusive way of using the pre-trained models, because you get the entire weight, and this entire weight is used to initialize the the model for some downstream tasks. And this downstream task will provide a supervision signal to fine-tune such models. And of course, there are fancy ways to do it too. So you can do partial fine-tuning, you can do low-rank adaptation, so on and so forth. And I think there are two dimensions that can help us group or to list these three ways of using pre-trained models. The one dimension is about effectiveness or customization, because if we have the weights, then we can do anything with it. We can customize it for very different tasks, and it can be more effective specifically for that task. But on the other side, there's also efficiency. So if you just freeze the model to compute features, it's more efficient. There's no training involved. If you just get the output, it's also very efficient. And it's also very secure to the model that, I mean, you just get the output. There's no weights leaked to the outside world. On the other hand, it's less effective because the pre-trained models are just pre-trained for certain tasks and not well-tuned for some downstream tasks, for some other downstream tasks. So the question we have when we wear this ablative research goggle is, do we really need all the features and the weights after we have pre-trained those models? So that's the motivation when we look into this space. So we want to remove the features and weights and see what's the minimum amount of information the pre-training will provide for downstream tasks. And I'll directly jump into the takeaway message is that we find attention is almost all you need from pre-trained vision transformers. And by attention, I mean you just need the attention map from those pre-trained models. So it's not the entire set of features, it's the attention map. And with enough attention maps, we can get most out of the pre-trained model. With one caveat, which is when the data distribution shifts. So for example, the pre-trained model was on this data distribution A, and then the downstream task is on data distribution B, then this method that relies on attention map is not as effective as tuning the weights or getting all the features. So what do we mean by attention map? So in a vision transformer, the attention map is inside this multi-headed self-attention block. And specifically, so there's QKV product, and the attention map is the product between Q and K transpose after some softmax. And I want to say that given a fixed attention map, all other operations inside the network are intra-token operations. So this includes the V operation, the O operation in the same block, and all the MLP blocks. So it's just computing inside each token. And in this way, attention map actually defines the inter-token operations inside the transformer. And when we do attention transfer, we are effectively decoupling these two types of operations. So we can do we can have a pre-trained vision transformer as a teacher. We get the attention map from there. Then the teacher provides these inter-token operations. And then a student VIT will learn the intra-token operations all from scratch. And we tried two variants. So one is attention copy, the other is attention distillation. They both fall within this paradigm of attention transfer. And for attention copy, it's very simple. So the teacher will provide this attention map to the student. The student directly copies the map and use it for all the inter-token operations. For the rest of the weights, the MLP weights, MSA part of the MSA weights, they will be trained from scratch. In this way, the operations are fully decoupled because the inter-token operation is exclusively from the teacher, but the student is learning all the intra-token operations. The second one is attention distillation. So the teacher will still provide the attention map, but the way the student uses it is via distillation. So it's again very simple. We just apply a distillation loss, like knowledge distillation loss, treating the attention map from the teacher as a target. And the student will also learn this attention map from scratch, but it receives supervision signals from both the task and also the attention map from the teacher. And the advantage for attention distillation is that it has the same testing cost. So in the previous case, attention map is provided from the teacher, the rest is from the student. So you have to forward two networks for the final output. But in our case, in the attention distillation case, after training, the student is able to stand alone. So you just forward the network once for the final output. And the surprising thing we find is that attention transfer can actually match the fine-tuning, the weight fine-tuning performance on ImageNet. So here the setting is that we have a model, VITL, VIT large, and with pre-training of masked autoencoding. So the model has 24 layers and 16 head attention per layer. I mentioned this just because we will do ablations about it, or analysis about it. And what we find is that on the left, this is our lower bound. There's no transfer from any pre-trained model. So the entire set of weight is pre-trained from is trained from scratch. On the right hand, it's a full transfer. So you get all the weights from the pre-trained model and then fine-tune these weights. And what we find that is that attention copy can recover 77.8% of the performance gap between no transfer and full transfer. And for attention distillation, we find it's even easier, that can get 100% of the performance gap when we do attention distillation. And this is actually faster as well, because you don't need to forward twice for the output. For analysis, we did some partial transfer. So for example, we can copy a subset of the layers. And we find that random attention map seriously hurts. So That means inter-token learning is very important. If you have a random attention map, then it is maybe 10% worse compared to the one with attention map supervision. And we find that more layers help, and it saturates at some point. So even if we tried 2 ways. One is to partial transfer from the top. The other is from the bottom. And 18 layers is already good enough for partial transfer. And we find that transferring top layers is more beneficial than bottom ones. So that means the attention map from the top layers are more important, like a more important knowledge from the pre-trained teacher model. It's harder to learn from scratch using a student model alone. We also did some comparisons between the attention transfer model and the pre-trained or fine-tuned model. So here, the horizontal axis is a layer index. So in total, there are 24 layers. And vertical, we do the CKA similarity there. It's a similarity metric, so the larger is more similar. And we find that the pre-trained VIT and fine-tuned VIT are similar in early layers. So this is a sanity check for us because the pre-training, so after pre-training, fine-tuning was only changing the layers. So the later layers, the similarity is low, but the initial layers, earlier layers, the similarity is very high. So this passes the sanity check. And what we find is that attention transferred and fine-tuned models are quite dissimilar. So it's even from the beginning that the CKA similarity is low. We also did this comparison by model ensembling. So you can fine-tune, you can ensemble fine-tuned models. Well, here it's ensemble in itself. We can ensemble the fine-tuned model and the attention copied model. We can ensemble with the attention distilled model. So in both cases, we find that it helps on top of each of the model. So attention copy is 85.1, gets a 1-point improvement, and attention distillation also gets helped. And the takeaway here is that the attention transfer-based predictions are not particularly correlated with the fine-tuned ones. So that's why example can help on top of it. So since we posted a paper, the original VIT author actually checked the paper carefully and proposed to add one more baseline here, which is to fine-tune twice and then do the example there. And we find that fine-tuning twice also helps. So there's some diversity over there for even if we fine-tune the model twice. We want to next, I want to present some results to show the generalization of it. So in terms of model size, we find that even with very limited search in hyperparameters, it generalizes well. For different pre-training methods, for example, muscular autoencoding, contrastive learning, vision and language contrastive pre-training, for all of these, we find that it generalizes well. So pre-training, you can just get attention from pre-training, and that can work. We see some mixed generation with pre-training data. So we tried pre-training on different data sets, and we find that it can hurt the performance, especially if we pre-train on COCO, then do attention copy, there's like a 2% drop with attention copy. And this is some mixed signal. And we also see mixed signal with the generalization on evaluation data. So here we pre-train on ImageNet, and then we only change the evaluation data. So these are all variants on ImageNet. And we find that compared to tuning, attention copy and attention distillation are worse, especially for attention copy. Um, um, and the only exception here is ImageNet v2, which we find is the closest in data distribution compared to the pre-training data. So in this case, it works well. But for others, where the data distribution changed, the performance is not that well. And the least amount of generation we see is that if we change both the training and the evaluation data. So here we change the downstream task to iNaturalist. So that's for fine-grained image classification. And we find we can never reach the fine-tuned model performance for both attention copy and distillation. So the takeaway here is that we see a high correlation between data distribution shift and the attention transfers performance degradation. And finally, with a few minutes left, I just want to talk about a third model, a third research where we just do ablation study all the way through. And this is removing things, that's why we call it deconstructing. So I just talk about the motivation, why we want to talk about this and the main takeaway. We all know that diffusion models work well, and this works well for image generation. But in our work, we want to see how much does it understand images. So there are famous quotes from Richard Feynman that if he cannot create things, that means that he cannot understand things. And there's different opinions, of course. For example, Yang thinks that if we want to do world modeling for some understanding tasks like recognition or planning, then maybe using pixel level pixel level prediction, which is generation of images, is a terrible idea. So we want to do an empirical study to see how much does diffusion model understand. And the way for measuring the understanding is via self-supervised learning. So this is a paradigm where one would pre-train representations without human annotated labels. So this is an unsupervised learning task. But we do not care about the task itself, the performance of the task itself. We care about the transfer result to understanding tasks, for example, object detection, classification, so on. So that means if we want to know how much does diffusion model understand, one direct way is to find a self-supervised learning component inside such models. And indeed, it is there because for diffusion models, for each step, it is essentially a denoising autoencoder that does the underlying work. So you have some noisy input as a noisy image as input, and then want to predict the clean output, or at least a cleaner output. And this is a classical denoising autoencoders at work. So here is a plot, well, a diagram showing the pipeline. So you add the noise to the input and the denoised as output. And this pipeline actually works quite well if we have masked noise. So you have an input, you mask out a lot of the patches and use the remaining patches to reconstruct the original image. This works pretty well. It's called masked autoencoding. It's also our previous work. But the diffusion case is adding noise. So the noise and signal are mingled together. So it's a different type of noise compared to masking noise. But in order to study how much does denoising play, how much of a role the denoising plays in the modern denoising diffusion models, it's quite complicated because the pipeline itself, this is the annotated version, is super complicated. Lots of components, and even if this model works for self-supervised learning, we still don't know like which one, especially whether denoising is playing a key role there for making the pipeline work. So our work was to do ablation to the extreme. So we deconstruct the modern DDM from the left toward a classical DAE on the right. And here is some deconstructive journey at the high level. So we initialize with a modern denoising diffusion model called a diffusion transformer, DIT. We reoriented it for SSL. We deconstruct the tokenizer, and then we finally we move as much as possible toward a classical DAE. And we keep track of the performance when we remove things. And the final outcome of this deconstructive journey is a method called LDAE, where L stands for latent, because we find that adding noise in the low dimensional latent space is crucial. So here, the simplest form we have tried was PCA. So you apply PCA to each patch of the image, add noise there to inverse PCA. So it's a still image, but it's noised, and then we let it go through this denoising autoencoder. And with this effort, we have drastically closed the gap to existing working paradigms, like masked autoencoding. So just to give you a glimpse of what we did, we tried various ways, actually 4 ways, to construct the low dimensional latent space using a tokenizer. The default tokenizer is a convolutional variational autoencoder. We deconstructed it step by step. So we have a patchwise VAE, so moving from convolutional to per patch. We do patchwise AE, so removing the variational part. We do patchwise PCA, so that's further removing the weights. So now it's a shared weight for the projection and the inverse projection. And there are different filters we get from different tokenizers. And we did the study for these 4 variants. We have 4 different latent dimensions. And we find that the performance trend is something like this on the right side. Note that for each patch, the original dimension is 784 or 68, I forgot, 700 plus. And here we find the latent dimension around 16 or 32 is the best. And this is regardless of the specific variants we have tried for the tokenizer. So that's why our takeaway is that latent noise is important. Okay, so yeah, so this is a message. We find that we can denoise in the low dimensional latent space, and these days it can be true even for image generation because latent diffusion models are popular, and pixel space generation is in general pretty hard um, for images. Okay, so I think I'm exactly on time. So today I talk about 3 episodes of ablative research. I talked about additive research that I typically do when I was a graduate school. I talk about ablative research, that's a main thing. And in the worst case, if ablative research does not work because there's no free lunch, you can try to start with removing components and see there's some alternative thing that can be added back in order to uh, offset the loss. Okay, that's it. Thank you.
Thank you very much. Questions? Yes, go ahead. Thanks for sharing this. I have a question related to the VQA system. It seems like you do some like exploration for the region proposal idea. I wonder whether like the method is, I mean the grid method is, the size of grid is also can be sensitive. Whether you are also exploring the size of grid will also like influence the performance, and whether you compare this kind of parameter with a number of region proposals.
I see. So in our study, we didn't change it. So it's always from the same scale, if that's what you are asking about.
Yeah,
Um,
yeah.
yeah, so
The
yeah,
size of grid may also influence the model performance a lot.
yeah, it could be. But we didn't try that. One of the reasons was that the grid features were also used to detect objects. So during the pre-training phase, when we pre-train the grid features, we will use one-by-one pooling to detect the objects. So compute the features from the grid feature map and to detect objects. And the object will come in different sizes. Uh, so this one-by-one pooled feature should represent the entire person. It can also be used to represent the head or part of the person. So I would assume that even though on the surface we are just using features from the same layer, but inherently it learns to be multi-scale. Uh, yeah,
And
well, but of course, intuitively, you can always add more feature maps and get it work. Yes.
another question is for the diffusion model for image.
Hmm.
Uh,
Hmm.
Normally, like for the self-supervised learning, we have like some pretext objectives. I just wonder what is the difference between the diffusion model for image generation and the diffusion model for the image understanding related to this kind of pretext objectives.
Uh-huh. Um, I think there are a lot of differences. So that's why um, when I talked about our overall trajectory, there's a very important step that we want to reorient this diffusion transformer for generation toward this task, self-supervised learning. The original diffusion transformer, it's not even a legitimate SSL pipeline because there are quite a few supervision signals there. It's not self-supervised. So we reoriented that. Um, and then I think since then it should be mostly self-supervised learning based. Um, I think for details you can check the paper. But yeah, there are a lot of differences. And in particular, we find that there's some trade-off between uh, this diffusion transformer and self-supervised learning. So the trade-off in design, like one design can be particularly good for generation, but it's not good for understanding. And if we tune the knob, then it will be better for understanding, but worse for generation. Yeah.
Okay, thank you.
Mhm.
Yeah, go ahead.
Yeah, I have a quick question here, and thanks so much for this very insightful talk. And I was wondering, your latent DAE work, especially for the patchwise PCA,
Mm.
do you have any results for it on like image generation task when using FID as an evaluation matrix? Because this seems like you can get rid of VQ-GAN, which is a training-based method. And a lot of time with latent diffusion model, you do need to have a VQ-GAN. But with patchwise PCA, it seems you can get rid of that training-based performance. In your slides, this is reporting the linear probing accuracy, right? I was wondering, have you applied in image generation tasks in terms of the FID score?
Yes. So in the paper, we talked about we reported the FID score in the beginning when using when the pipeline is still quite close to denoising diffusion models. But once we have switched to that, we didn't measure FID. So for the final pipeline, for PCA, we didn't have a FID result. But since then, I moved on to do some ablative research to tokenizers as well, so I can comment on that as well. I would say the encoder for the VQ-GAN, it doesn't matter that much. The decoder is the one that actually do the job for making the generation, beautiful or authentic or faithful to the image. So my current hunch is that for encoder, we can actually use the PCA basis, and most of the work can be shifted to the decoder. And whatever image generation pipeline that's plugged into this latent space, it can operate on this PCA space. And then for the decoding, like once the diffusion modeling is done, you get the output, and then you can have a more powerful decoder with GAN, with LPIPS loss, with all of those, and still generate visually pleasing images. Yeah, that's my current take on this.
Just a follow-up question here. So I guess there might be some misunderstanding here. So when you talk about you destruct the embedding of tokenization here, you are talking about you basically replace the how you project into the latent space for doing the latent diffusion model. That means because when we do the latent diffusion model, we have a pre-trained autoencoder, right? The encoder project image into a latent space, and the decoder map whatever you generate in the latent space to the image.
Yes.
Right? So we
Yes.
have the diffusion process in the latent space. So you are talking about basically just replace the encoder and decoder part, but the diffusion process, which happens in the latent space, is still there, right?
Yeah, so I'm talking about two different things. So here, the latent DAE pipeline, we immediately map the noised PCA projections back into the image space. So
Right.
in this case, it is indeed image space, denoising. I will call it denoising. And this is for image understanding. But when I was addressing that question, I was talking about image generation. And for the image generation pipeline, my current hunch is that you can do PCA as an encoder, and do the latent space diffusion modeling there, and
So, right.
and then plug in a powerful decoder equipped with GANs, equipped with like perceptual loss, and I think that can work and achieve a good FID score. Yeah.
Okay. Let me plug in the last question because we don't have much time left.
Okay.
You talk about the second part when you talk about you call it attention copy, right?
Yeah. Attention transfer, attention copy, and
that's really striking. I mean, that actually work. Do you have any intuition why that could work? I mean, I know that's not the best one, but still, it's very striking that it works to some extent. Do you have any intuition why that's the case?
yes. So, I think the biggest intuition is that so the pre-training is mostly figuring out the inter-token communications. And that's a hard part for learning.
But I mean, when you have distribution shifting, you can give your features from your the part the token part, because this is about how do you build a relationship between the tokens, right? If your token change, there's no reason to believe that the relationship should be similar, right? So
well, yeah, well, I think it's called self-attention for a reason, right? So the QK map, here, it will tell the student model that for this layer at this point, you should pay more attention to certain locations of an image, right? And of course, the student can learn to ignore that. The student can also learn to leverage that information. But the information is there that the teacher will say that the attention map tells me that when you do the computation, please pay more attention to that token, that location. So yeah, so
it's very striking because by the way, just to clarify that I got it right. So you do this, your data actually has gone through some distribution shift, right? You're assuming there's some distribution shift. Or
yes. Well, I think
some disconnect without any distribution shift.
So here, when I show the results, here, there's no distribution shift. Sorry for the confusion. So we have ImageNet 1K that's being used to pre-train masked autoencoding, and it's also used like as an evaluation for classification. So in this case, there's no distribution shift. And I talked about, the distribution shift is the most salient like bad thing for generalization, that like even if we evaluate on some other distribution changed data set, it's not as performant as tuning.
I see.
Mhm.
All right. Thank you very much. I think there's a lot of interesting observations. I think that's really thought-provoking. Thank you very much, Xinlei, and have a nice day.
Thanks, you. Yeah, thanks. Have a nice day.